Welcome to the Electrical and Electronic Engineering Lecture Series. Your anchor person is Professor Michael Sindinechi. Our topic today is Engineering Lecture Series Self-Test, Part 7. Please follow me in the Engineering Lecture Series by subscribing to my YouTube channel at https://youtube.com/@Ndinechi-Michael-C. Like, share, and drop your comments in the comment section or reach out to me using my email addresses. To learn more about the topics that the self-test covered, go to my YouTube channel above and check out Module 026 and Module 028. Thank you for being part of the engineering lecture series. Like we said, it is always good for you to carry out a self-test from time to time to see how you understand the lecture and any topic. In our self-test today, we'll be covering areas of coding in communication systems and pulse modulation, including pulse code modulation. So let us go. Question 1. What do you understand by pulse modulation? Briefly explain the three main types of analog pulse modulation. And the answer is the process of transmitting the discrete sampled signal is termed pulse modulation. The three main types of analog pulse modulation are: 1, pulse amplitude modulation, also known as PAM. And we say here, the amplitude of the carrier pulses are varied by the sampled input signal. The shape, that is the width of the pulses, remains unchanged. The second one is the pulse width modulation, which is also regarded as the pulse duration modulation or pulse time modulation. So any of the three can be used because they are talking of the same thing. So some people prefer calling it pulse width modulation. Some people prefer calling it pulse duration modulation. Some call it pulse time modulation. Whichever one, they are the same. We say here, the trailing or leading edge of the pulse or both are made to vary as a function of the sampled input signal, thus modulating the pulse duration or width while the height remains unchanged. The third one is the pulse position modulation, PPM. The pulse position modulation is the scheme in which the amplitude and the width of the pulses are kept constant while the position of each pulse with reference to the position of the reference pulse varies according to the instantaneous sampled value of the message signal. Question 2. What do you understand by pulse code modulation? So, if the sample signals are quantized and each quantized sample represented by its binary equivalent as on-off pulse sequences. Then the resultant output is referred to as pulse code modulation. 3. Using a block diagram, describe the working of a pulse code modulation system. So we are looking at the block diagram. So you see that at the transmitter end, you have the analog signal, which you want to convert to its digital equivalent and transmit. So the analog signal comes in and it is filtered to remove ripples. Then it is sampled. The sampler samples the signal. After sampling it, it is fed into the quantizer. The quantizer will now, as we go on, we will see the actual work of the quantizer. It will try to get the values of the signal at different points and code them into their binary equivalent using some techniques. So those binary bits equivalent to the amplitude of the signal selected at different points are encoded by the encoder and transmitted out. So at the receiving end, the decoder will do the reverse process of the encoder, and as it is doing that, the holding circuit is holding them. Depending on the timing, it will be now sending that to the filter, which now gets back the equivalent of the filter in the transmitting end. So that is basically that. So we go on to now explain the block very well. So from the block diagram above, the continuous signal is first low pass filtered, sampled, and then rounded off or quantized to the nearest predetermined discrete amplitude level to give a digital signal that is discrete in time and amplitude. The encoder converts the quantized samples to the digital code words on a code word per sample basis. You can see that on code word per sample basis. We have talked about code words to represent the number of bits that is used by that system to represent a word. So at the receiver end, the decoder does the reverse process while the holding circuit reconstructs the signal, which is then filtered to give the output. So now, question 4. What do you now understand by the term dynamic range of a pulse code modulation system? I would say that the dynamic range of a pulse code modulation system is the ratio of the largest amplitude to the smallest possible magnitude that can be decoded by the digital to analog converter, which is used in any particular PCM systems. Now, it is important for us to mention something here because we've been hearing of filters. Sometimes we talk about low-pass filters, we talk about high-pass filters, we talk about band-pass filters, we talk about band-stop filters. Now, a low-pass filter is always represented in a circuit by that symbol where you have three of that, alternating voltage current symbol. The lowest one has no line crossing it. The two up ones have line crossing them. So they are called low pass, meaning that it passes signals from 0 to a particular point, and from that point up, it doesn't allow the signal to pass. So it's a low pass filter. It allows lower signals from 0 to a particular point to pass. So the second symbol, which is the high pass filter, shows the reverse of the first one, where the first two from down has line crossing, showing that the system will not allow signal to pass until it gets to a certain point. From that point, it allows the signals to pass. So we call it high pass filter. And the symbol is that. We also have the third one, which is the band pass filter. The band pass means that it stops signal from 0 to a point. Then from that point, it allows signals to pass to another point. Then from that other point, it will also not allow signals to pass. So it is called band pass filter. And the symbol is like that. And the fourth one is the band stop. So it will allow signals to pass from 0 to a particular point. It will not allow signal to pass until a certain point, and it will continue to allow signal to pass from certain points. So you see that the band stop is almost the reverse of the band pass filters. So in your communication circuits, you will not always hear people talking or writing low pass filter, high pass filter, band pass filter, or band stop. They will just use the symbol you are saying to represent. And as a communications engineer, anytime you see that, you know exactly what the person meant. So, question 5, so what do you understand by the terms quantization, quantization error, and quantization noise? So, when we were looking at the block diagram of the pulse code modulation system, we saw the quantizer. So now the quantizer is quantizing the signal. And the question here is, what do we mean by that quantization? So we say that the process of rounding off the values of an analog signal to approximately its stabilized value is known as quantization. Now, when the quantized signals get to the receiver, they are demodulated or reconstructed by essentially the reverse set of operations used at the transmitter. The reconstructed signal is then low pass filtered to eliminate sampling harmonics. Since the reconstruction cannot be perfect, a difference exists between the reconstructed signal and the ideal signal. This difference is referred to as quantization error. So, put simply, you are receiving a signal and sampling it and taking bit by bit of it to transmit. At the receiving end, you try to reconstruct. There is no how you can get back all the signals because you are taking certain value of the signal at certain points. The point before it and the point before the exact place you're taking samples from may not be exactly the same. So by the time you are reconstructing, you will not get back exactly what was imputed at the transmitting end. So that small differences will constitute an error by the time you finish reconstructing the whole thing. That error is called the quantization error. And this quantization error is associated with additive noise, which is a random process and is referred to as quantization noise. I want you to get it. You get a signal, you take different points of it and convert to its binary equivalent. That is the magnitude of it. Now, if you convert it, you transmit. At the receiving end, you try to reconstruct. It will not be exactly what was fed in. Because it is not exactly what was fed in, it becomes an error. So that error you call quantization error. But because this error is cumulative, it occurs at every point you are doing this, at every point you are reconstructing. You now say that this error, when you add all of them, it will appear in form of noise in your system. And that error, which when you add all of them becomes something like noise. When we say noise in communication system, we mean unwanted signal. Then it becomes quantization noise. So this quantization noise is most serious when the signal is small and covers only a few of the lower quantizing intervals. For instance, when you are talking, you can see that the signal your voice is producing is not having very wide, difference between the peak and the lowest um, portion of it. So when you try to quantize that, you will now have serious difficulty because it will look as if you are just having a flat or a straight line signal. So you say that quantization noise is most serious when the signal is small and covers only a few of the lower quantizing intervals. So there is also how to overcome this by doing delta modulation. So we will see that later. Now, question 6, explain the term multiplexing. So the term multiplexing is used to describe the technique used in sending a number of separate signals together over a common communication channel and doing that simultaneously without interference. The device that does this is called a MUX or a multiplexer. The reverse process of extracting the number of signals from one multiplex channel at the receiver is known as the multiplexing, and the device that are used to do this is called the multiplexer, in short, the MUX. Question 7, what are the two classes of analog multiplexing systems? Explain the features of each. So say that there are two classes of analog multiplexing, and they are frequency division multiplexing, known as FDM, and the wavelength division multiplexing, known as the WDM. In FDM, the available bandwidth of a single physical medium is subdivided into several independent frequency channels. Independent message signals are translated into different frequency bands using modulation techniques, which are combined by linear summing circuits in the MUX to a composite signal. The resulting composite signal is then transmitted along a single channel. At the receiving end, the signal is applied to a bank of bandpass filters, which separates individual frequency channels. The bandpass filter outputs are then demodulated and distributed to different output channels. If the channels are very close to one another, it leads to interchannel crosstalk known as aliasing. In our previous self-test, we have talked so much on this aliasing. So the effect of this aliasing is sometimes the crosstalk. It leads to crosstalk. And we will, at this point, want you to, look up this term, crosstalk. You can see that it can be a near-end crosstalk, it can be a far-end crosstalk. Please look it up. In our subsequent lectures, we will also be talking about crosstalks. So, in the WDM, that is wavelength division multiplexing, many signals of different wavelengths are transmitted in the light spectrum. It is conceptually the same as FDM, except that it operates at very high frequencies. Very narrow band of light signal from different sources are combined to make a wider band of light. At the receiver, the signals are separated with the help of the multiplexer. Optical fiber communications use this wavelength division multiplexing technique to merge different wavelengths into a single light for transmission. If you recall your basic physics, when you use your prism to direct light, that is exactly what happens here. Question 8. How does the orthogonal frequency division multiplexing work? So the orthogonal frequency division multiplexing, or FDM, technology transmits multiple signals simultaneously over a single channel, with each signal traveling within its own unique frequency range, which is the carrier, modulated by the data. OFDM employs the spread spectrum technique. In future, we'll be seeing this spread spectrum technique, how it works. But here, OFDM employs it to distribute the data over a large number of carriers that are spaced apart at precise frequencies. So this spacing provides the orthogonality which prevents the demodulators at the receiving end from seeing frequencies other than the one meant for them. It is similar to FDM but has much more spectral efficiency by spacing the subchannels much closer. This is done by finding frequencies that are orthogonal, that is, frequencies that are perpendicular to one another in the mathematical sense, thereby allowing the spectrum of each subcarrier to overlap another without interference. In other words, what you are saying here is that the OFDM will basically operate that there is translation that is done the frequencies, and the receiver becomes blind to all other frequencies other than the one he wants to see. We can draw an analogy here. If a design is made to see only black colors, it is possible now to transmit other things which is the same but using red color. That system cannot see that thing until it becomes a black color. That is exactly how this OFDM works. In other words, you can now transmit the same thing or different things using the same frequency but paint them different colors. So at the receiving end, each of the receiver is meant to see a particular color. So it sees only that color and be blind to other colors. Question 9, what are the advantages and disadvantages of this OFDM over FDM? So 1, OFDM has the following advantages, which is high spectral efficiency. Because it's not seeing the things differently, so you can use one bandwidth to transmit as many signals as possible. 2 is resilience to RF radio frequency interferences. It's possible to eliminate inter-symbol interference. We will get to know about inter-symbol interference when we look at wireless communication systems. It is used in broadband wireless access systems, used in wireless digital radio and TV transmissions, allows design of single frequency networks where several transmitters send signals simultaneously at the same frequency. But it has a disadvantage of being sensitive to Doppler shift. In future, we will also look at this Doppler shift in full, more especially when we will be treating radar systems. Question 10, explain the workings of the time division multiplexing. The time division multiplexing, TDM, is a digital multiplexing technique in which all frequencies or all signals operate with the same frequency but at different times. Each connection occupies a portion of time in the link. An electronic commutator sequentially samples all data sources and combines them to form a composite baseband signal. This composite signal travels through the channel and is demultiplexed into appropriate independent message signals by a corresponding commutator at the receiving end. Question 10. Differentiate between synchronous and asynchronous time division multiplexing. So in the asynchronous technique or asynchronous multiplexing, the sampling rate is common for all signals, and hence the same clock input is given. The time slots are transmitted irrespective of whether the source or the sources have any data to send or not, thereby leading to the wastage of channel capacity. So we are saying in the asynchronous, assuming you have 5 different channels to get information from there to transmit, it will sample 5 of them. Even if there is no information for any of them to transmit, it will still allocate its space and transmit nothing on its behalf. So at the end of the day, it wastes the channel capacity. We will see an illustration very soon. So in the asynchronous TDM, which is also known as the intelligent TDM, time slots are allocated dynamically based on demand, thereby saving the channel capacity. The multiplexer scans the input terminals, collecting data until the frame is filled and then transmits the frame. At the receiver, the multiplexers or the multiplexer, the MUX, receives the frame and distributes the data to the appropriate terminals. So, question 12. This is an illustration. So the figure below shows a high-speed multiplexer accessing 4 input lines from time T0 to T4. Show the frame output for the synchronous and asynchronous TDM. What is the percentage savings in the number of slots from using the asynchronous TDM? Now, if you look at that, let's cool down and follow that. You see the high-speed multiplexer that has input lines A, B, C, D. So you can see the commutator arm accessing the 4 input terminals. Now, from the figure on the left, T0 to T4, you can now see for the synchronous multiplexing, the commutator in A, we see those bands that are in orange color. So from T0 to T1, it will see something in A. So he calls it the A1. If you look at the first frame there, he calls it A1 in frame 1. It comes to B. From T0 to T1, there is nothing in B. It transmits an open space. That is why we put it as dots. Then it comes to C. It sees the green data, so it takes it as C1. By C1, we mean the first data it is getting in C. It gets to D, it sees nothing. So even though there is nothing in the B and D slot, it still transmits that empty slot as frame 1. It goes back to T1. From T1 to T2, the input terminal A has nothing to transmit. So instead of leaving it, it still transmits an empty space. For B, T1 to T2, it sees the first data, which is that purple. So it calls it B1 because that is the first data it is getting in the B channel. Then T1 to T2 under C, that is the green, it sees nothing. It transmits nothing, but the space is occupied. It does that for D. It sees the, okay, maybe we call that the purple color, or which color, the brown color. So it sees the first thing in D, so it calls it D1. It repeats the thing from T2 to T3. So A has something which he calls now the second A, A2, because this is the third frame now. He sees something in B, he calls it B2. He sees something in C, he calls it C2. There is nothing in D, so it transmits empty space. Likewise, T3 to T4, which is the frame 4, it sees nothing in A, it transmits open space in A. It sees the second thing in the third time, it sees something in B, it calls it B3. The third time it sees something in C, that is the green, it calls it C3. And this is the second time it sees something in D, the brown something, it calls it D2. Now, you can see that from T0 to T4, it has 4 frames transmitted. But when it comes to the asynchronous one, you can see first in A, T0 to T1, it sees something in A. The second one, B, it didn't see something. Instead of transmitting open space, it continues to look at C. He sees something in C, because it's C1. In D, he didn't see something. He goes back again and scan. In A, he didn't see one. In B, he sees something, which is the first time he's seeing B, he calls it B1. In C, he didn't something. Instead of transmitting open space, he goes to D, he sees something, he calls it D1. So until that frame 1 is filled up, it will not transmit. So when frame 1 is filled up, it transmits the first set of frame. So it does the same thing for frame 2. By the time it gets to half of frame 3, it has covered all the input lines A to D that has something to transmit. So you can see that it's now using 2.5 frames to transmit what the synchronous is using 4 frames to transmit. So we say that it is having service of this number of slots, or 1.5 frames. So it said from the illustration above, the synchronous TDM uses 4 frames and 16 slots to transmit, while the asynchronous TDM uses only 2.5 frames of 10 slots to carry out the same transmission. And if you do that mathematically, you see that it gives 37.5% savings in slots and hence bandwidth. So, question 13, what is the basic aim of any communications system? Of course, the basic aim of any communication system is to provide error-free and secure transmission of information from one point to another. Now, state 4 classes of coding in communication engineering. The first one is data compression, that is to reduce space occupied by the data stream. Second, data translation, that is to change the form of representation of the information so that it can be transmitted over a communication channel. 3, error control, that is to encode the signal so that errors can be detected and corrected. And 4, encryption, to encrypt information for security purposes. Question 15. Now, if you're given 4 numbers, 25, 27, 23, and 21, to transmit in digital format, Show the sequence of bits you will transmit using parity check for error control. We have said that you use parity checks, or you pad your system with parity checks, so that at the receiving end, the system will scrutinize the parity checks and use it to know whether the string of ones or string of zeros that are contained in what you transmitted is what is supposed to be. If it is not what is supposed to be, automatically means that there is an error. And if you do some further processes, it will now show you the bit that is in error. And if it is bit 0 that is in error, then the system on its own changes it to 1. Immediately it changes it to 1, it means that it has been able to detect the error and correct it. And that is the principles of error detection and correction. So first, convert each number to its binary equivalent to get the informational bits. The simplest parity check involves a count of the numbers of ones in the informational part of the code word. If this count is even, a 1 is inserted as parity check digit. If it is odd, then a 0 is inserted instead. Remember, this is standard. As a designer, you can decide to, state your own terms and reverse this depending on what you want to achieve. So the numbers given to us, we see that if we convert 25 to its binary equivalent, it will give us 11001. And that is the information we want to transmit. Now, we count the number of ones in that 11001. You can see that we have 3 1 bits. Then, what do? We append a 0 as parity, since the number of 1 bits is 3, which is odd. Then when we append that 0, it gives us 110010. We show that parity bit by putting it in italics and in color. So when we do 27, we also get 11011. Just convert 27 in decimal to binary. Straightforward thing to do. When you do that, you see that the number of 1 bits will be 4. So because it is 4 even number, you append a 1. Then you convert 23. You can also see that the number of bits is of 1 bit 4. So you append a 1 because the number of 1 bit is even. 21, when you convert, you have the same thing. So what will be transmitted will be now 6 digits. Each of the 6 digits will represent the parity bit. So what will be transmitted will be 110010, that is the parity bits, 110111, 101111, 101010. So that is what will be transmitted using the parity check to do that. So 16, state the general format for a 4 information digit Hamming code. Show how the parity check digits are computed from the information digits. Of course, the Hamming code is a systemic code that helps you to, spot bits that are in error at the receiving end. That is, you transmit, we have said For channel coding, you add redundant bits to help you detect when there is an error in the signal or the signal you sent or digital signal you send to the receiver through a channel. So now, using the Hamming code, that redundant bits are represented as C0, C1, and C2 for a 4-digit informational code, which is I0, I1, I2, I3. So he puts it in that format as C0, C1, I0, C2, I1, I2, I3. You say where the digits I0, I1, I2, I3 are the information digits, while the C0, C1, C2 are the parity check digits. So these parity check digits are computed using or computed from the 4 information digits as follows, and that is done using a modulo 2 arithmetic as follows. C0 is equal to I0 modulo 2 I1 modulo 2 I3. C1 is equal to modulo I0 I0 modulo I2 modulo 2 I3. C2 is equal to I1 modulo 2 I2 modulo 2 I3. So we now say from our example, if we have a 4 information Hamming code as 1010, find the code word to be transmitted. Remember, the information bit is 1010, meaning that I0 is 1, I1 is 0, I2 is 1, I3 is 0. So you now compute the C0. If you look at it, don't be scared. It's as simple as A, B, C. So you compute C0, which is I0 modulo 2 I1 modulo 2 I3. So I0 is 1, I1 is 0, I3 is 0. Now, 1 modulo 2 0 is what? 1. Then the 1 modulo 0, modulo 2 0 is also 1. So you see the first one is 1. The second one, C1, is I0 modulo 2 I2 modulo 2 I3. Then that gives you 1 modulo 2 1 modulo 2 0. And the answer is 0. C2 gives you also 1. Now, if you look at it, you see that when we were treating the logic gate, modulo 2 is the same as the exclusive OR gate. And in the exclusive OR gate, we drew an analogy that the gate is like when you have an automatic gate that opens only when one person is at the gate. If there is no person, the gate will not open. If there are 2 people, the gate will not open. That gate opens only when it is only one person that is standing by it. In other words, if we do a truth table for an exclusive OR gate, which is this modulo 2 arithmetic, we say that it gives an output 1 only if one of the inputs is at the 1 state. So if we get back to this and look at that C naught, which is 1 modulo 2 0, if you do that, it's one of the inputs that is at 1, so it gives you output 1. Then you do again 1 modulo 2 0, which gives you output 1. It gives you 1. The second one, C1, 1 modulo 2 1 is equal to 0, which is the same thing as 1 exclusive or 1, which gives you 0. Also, 0 exclusive or 0 gives you 0. You can see why C1 there is 0. And C2 is 0 modulo 2 1. It's only one output, only one of the inputs is in 1 state, so it gives you the answer 1. Then 1 modulo 2 0 also gives you 1. You can see why C2 is equal to 1. So the code word now becomes from what we had before, which is C naught C1, I naught C2, I1, I2, I3. So you can now see from what we have here, C naught is 1, we put the 1, C1 is naught, is 0, we put the 0, I1, I naught is 1, from the information bit, I naught is 1, you put that. C2 is what? 1, you put the 1. I1 is 0, you put the 0. I2 is 1, you put the 1. I3 is 0, you put the 0. So this is what your code word will be transmitted. In the real sense, if you transmit this bit 1011010, and along the line there is an error in one of them, probably due to degradation, interference, or whatever, and one of these bits, let's say the last one, which is 0, is received in error as 1 in the receiver, the system will automatically identify that that bit, which is the the least significant bit of that 1011010, is received in error. Since it is received as 1 and it is in error, it means that automatically it should have been a 0. So the system on itself will convert it to 0. By doing so, it has automatically detected the error and corrected it. Because if it sees that 0 is in error, then to correct it will be to make it a 1. And that is one of the beauties of digital systems, why they are simple and helps in error detection and correction. So thank you once more for going through the self-test with me. It will assist you to evaluate yourself and evaluate your understanding of the topics we have treated, more especially in multiplexing, pulse code modulation, and coding in communication systems. We hope that you'll find this useful in your exams, because the questions tend to bring out all the explanations that will be given in those lectures. But before we go, I want you to know, as a student listening to me, that opportunities are time conscious. If you waste your time, the train carrying them will pass. So you have to be time conscious to meet your opportunity. You have an opportunity to do something. If you don't do it on time when you're supposed to do it, then you miss it out because opportunity moves with time. For instance, if you're having, exam to face and you have things to read to prepare for that exam, it is an opportunity to meet what will help you to do the exam. But if you are delaying, keeping it later, you will see that by the time you are coming, that opportunity has passed and you will not be able to get it again. So thank you for listening. Please subscribe to my YouTube channel so that you will always get notifications when we have new lectures to do. If you were unable to join in these live lectures, please, it is replayable. You can now replay and listen to the lectures. Thank you.